Alright, welcome back to another business calculus video. In this video, we are going to be talking about evaluating definite integrals, which are basically just some properties of definite integrals that allow us to more quickly evaluate them, sometimes without having to resort to the fundamental theorem of calculus, and yeah, just making things easier for us in general. So, let's start by listing a few key properties of definite integrals. Alright, property one, I suppose I should give us the setup. Let f and g be integrable on a to b. So we have two integrable functions on an interval. Then, what follows? Well, first, we have a scalar multiple rule. The integral from a to b of c times f of x dx is c times the integral from a to b of f of x dx, and we have a sum rule. The integral from a to b of f of x plus g of x dx is the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Same holds true for minus. Alright, and I think we used both of these properties without formally stating them in the previous video, but they are true. Just like with indefinite integrals, scalar multiples pull out of definite integrals, and sums and differences also pull out of them. The important thing to remember when you do this is whenever you split up integrals like this, you have to keep the bounds on both of them. You'll never have just one definite integral being added to an indefinite integral. That kind of doesn't make sense, since this we're trying to work with numbers and indefinite integrals are families of functions. So, in general, anything you do with definite integrals, you want to make sure to keep the bounds in place. But definite integrals have some other properties that are very specific and depend on it being a definite integral and not just integration in general. So let's list a few of those. The integral from a to a of fx dx is equal to 0, no matter what the function is. And you might say, okay, well, what is going on here? We're integrating from the same lower bound to the same upper bound. In other words, if you try to view this as area under the curve, if you let a be here, we're integrating from a back to a. So we're just staying right there, which means we're trying to find the area of a line. But lines have no area. They have length, but no actual area. Therefore, 0. Alright? What's another property that definite integrals specifically have? The integral from a to b of f of x dx is negative the integral from b to a of f of x dx. Basically, if you sweep through the integral going from left to right, it's negative going through from right to left. And you can also see that this fact is true using the fundamental theorem of calculus. If capital F is an antiderivative of little f, then what happens? Well, the integral from a to b of f of x dx is f of b minus f of a, which is negative f of a minus f of b. But now hitting this interior part with the fundamental theorem of calculus, this is negative integral from b to a of f of x dx. So, geometric reason that this property is true, that the integral cares about whether you sweep from right to left or left to right. And the algebraic reason this is true for all functions with an antiderivative, fundamental theorem of calculus takes care of it. Alright? And you might say, okay, cool, I believe you that this fact is true. Why is it useful? We'll see that in a bit. So I promise this isn't just me saying, oh, look, we can do this for no reason. Okay, and then fifth property that definite integrals have, the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx for any c in between a and b. And our picture for what's going on here is saying, well, let's think of it again as area under the curve. We have our function f going between a and b, and we're trying to find this shaded area right there. That's what the integral is trying to measure. But what this property is saying is, hey, if you want, you can always split the integral at some point c, and the entire area under the curve is the same as this area plus this area. So the entire area corresponds to the integral from a to b of f of x dx. This area corresponds to the integral from a to c of f of x dx, and this area corresponds to the integral from c to b of f of x dx. And therefore, you can just add them together, right? It's very clear that these two areas add up to make the whole thing, and therefore the equality holds. All right, so those are some key properties of definite integrals. These two, same as indefinite integrals. These three, special for definite integrals. So let's see really, where did these three come into play and make definite integrals something to work with? We're going to develop two different primary methods for evaluating definite integrals. Method one, we've already talked about. Method one is you find an indefinite integral and apply the fundamental theorem of calculus. Okay, so let's do an example of that. Let's say, for instance, we want to evaluate the integral from 0 to 1 of x times the square root of 4 minus x squared dx. All right, so we're going to have to make a u-sub. Pretty clearly, the u should be 4 minus x squared, but we don't yet know how u-subs play with the actual boundaries of our integral. That'll actually be our second method, is talking about how that works. So for now, what we're going to do is we're going to move over to indefinite integral land, say, hey, the indefinite integral of x times 4 minus x squared dx, that's something we know how to deal with. Let's make our u-sub. U is equal to 4 minus x squared. And then du would be negative 2x dx. I see that there's a negative 2x, and we just have an x. So let's use our classic little trick of multiplying in. Negative 1/2 times negative 2 is equal to 1. Therefore, we can do that. And now we can apply our u-substitution. Getting, this is the integral of negative 1/2. This is the square root of u. And the negative 2x dx is du. Or in other words, negative 1/2 times the integral of u to the 1/2 power du. Power rule then tells us this is negative 1/2 times 2/3 u to the 3/2 plus c. Multiplying those and substituting in gives us -1/3 times 4 minus x squared to the 3/2 plus c. That's our indefinite integral, but we want to evaluate this definite integral. So now what we're going to do is we're going to apply the fundamental theorem of calculus. Which says that you can choose any antiderivative you want. So we'll just choose c is equal to 0. So by the fundamental theorem of calculus, the integral from 0 to 1 of x times 4 minus x squared, square root of 4 minus x squared dx is -1/3 times 4 minus x squared to the 3/2 evaluated from 0 to 1, which is -1/3 times 4 minus 1 squared to the 3/2 power minus -1/3 times 4 minus 0 squared to the 3/2 power. Using that standard notational trick, which just says, hey, you sub it in for the first one, subtract the second one. Okay, let's do some algebraic simplifications. This is -1/3 times 3 to the 3/2 power. Or in other words, -3 to the -1st times 3 to the 3/2 power, just for the sake of being able to merge those exponents later. Minus -1/3 is plus 1/3 times 4 to the 3/2 power. If you just left it like this, that would have been perfectly fine. Even if you just left this as a 1/3, that would have been completely okay. But we can actually do a little more simplification. Exponent rules tell us that this is -3 to the 1/2 power. 3/2 minus 1 is 1/2. Plus 1/3 times 4 to the 3/2 is the square root of 4 cubed. So this is what's 3 to the 1/2? That's the square root of 3. Plus 1/3 times the square root of 4 cubed is 64. That's a perfect square. So this is -square root of 3 plus 8/3. Or if you want to rewrite it, 8/3 minus the square root of 3. If you check, you'd find this is a positive number, which makes sense because we're trying to measure a function that would be completely positive between a positive and a negative. Okay. That's all good for us. That's method 1. And it works just fine, right? Step over to indefinite integral world, get your antiderivative, apply the fundamental theorem of calculus. Nice and straightforward. But you might ask yourself, well, okay, I just don't like having to step over into indefinite integral world, right? Like, sure, it works, but can I make this any quicker? And the answer is yes. And that's going to be our second method of evaluating definite integrals, is a method where we can stay in definite integral world the entire time. So we're going to do another sidestep example, and then we'll come back to this one and do the exact same thing. So save this number. We should get it again. So, method 2 for evaluating definite integrals is going to be stay in definite integral world. All right, so what kind of thing do we have to do to make that happen? We use a U-Substitution, and that was kind of the key part, right? If no U-Subs go on, we already know how to stay in definite integral world. We can just split up the integrals using the sum rule, everything like that. Everything works great. But what do we do if we need to use a U-sub to evaluate the integral, and we want to stay in definite integral world. So let's geometrically see what is happening with a U-substitution in definite integral world. Let's say we have f of x equal to x plus 1 squared. And fx on x plus 1 squared is going to look roughly like this. Here's -1, here's -2, there's 0, there's 1, so on and so forth. So let's say we wanted to find the integral from -2 to 1 of x plus 1 squared dx. Then what we're really going for is we're going for this area here. Should be symmetric, but no. Or not. Would that be symmetric? No, it wouldn't. This should curve up much, much higher. And this should be much lower. Sorry, I got pedantic and I was like, well, I should probably shade in the actual area that we're going for. Alright, does that show up clearly on the video? Yes, it does. How about that? Alright, so we're really going for that area there. The function continues up like this. So, if you were trying to do this, you would say, okay, well, I'm going to make my U-sub. If I make the U-sub u is equal to x plus 1, then du would just actually be dx. And so the U-substitution becomes some integral of, well, u squared dx is just du. Nice. But what should the boundaries be? Because here's the key part of a U-substitution. This is an integral with respect to x. We're thinking about what happens x is x goes, what happens f of x really, as x goes between -2 and -1. I'm going to label these axes. I don't normally do this, but it is important here. We are in the xy plane here. But when we do a U substitution, we're now taking an integral with respect to u, a new variable in terms of x. So geometrically what's happening is we're shifting over from an xy plane to a y plane, and we're geometrically transforming the function. So now instead of x plus 1 squared, which has a graph like this, we have u squared. This graph looks like this. So same idea, it's just shifted over 1, because that's what our u sub said to do. You shift it 1 to the right. So now we have our u substitution, and it wouldn't make sense for me to trace the same boundary. So here would be -2, here would be -1, here would be 1, and then here would be 2. If I did the same -2 to 1 interval, the area is wrong. The shape is different, right? And because of the symmetry here, you might end up with the same number if you did it just by sheer luck. But really, this is incorrect, right? This is the wrong shape and a more complicated function that would completely screw over the area you're trying to compute. Or if we had just even changed the balance, that would have completely screwed over the area you were trying to compute. So how do we get the same shape? Well, it looks like the corresponding shape is between -1 and 2. Looks like that's the corresponding shape, which means that's the number we're trying to go for. We're trying to go for that area. So this should somehow now be the integral from -1 to 2. Because now, instead of taking integral with respect to x, as x goes from -2 to 1, we want the integral with respect to u as u goes from -1 to 2. Okay, but we find out what those boundaries should be? Like, it makes sense when you draw the picture like this that we're just shifting it over, but I don't have time to draw 2 pictures for every single function I do, especially really complicated, really difficult to graph functions. How do we actually figure out what those areas should be? Great question. So, to kind of summarize what we've talked about so far, we've stated that when you do a U-substitution with definite integral, if you want to stay in definite integral world the whole time, you need to change the boundaries of your integration. How do you figure out what those new boundaries should be? What we're going to do is we're going to just plug the old boundaries into our U-substitution, and that'll tell us what the new boundaries are, because the boundaries in X, if I want to transform them to U world, I run them through the same transformation as everything else, and now it tells me what those proper locations should be in U world. So, for instance, if we let UA be our new lower bound, and UB, U sub B, be our new upper bound, and I'll just use this notation in general, where if I say it's something sub A, that means it's a new lower bound in terms of this variable, and sub B will mean new upper bound in terms of this variable. With this substitution, U sub A, let's say, to make sure we all know we're working with this substitution. In this case, U sub A would be the old X sub A plus 1. Or in other words, negative 2 plus 1, which is negative 1. And U sub B will be X sub B plus 1, because that's the transformation we're working with. And this would give us what? Well, X sub B plus 1 is 1 plus 1, which is 2. So now we'd say, oh, the integral should be going from negative 1 to 2. But look at that, that's exactly what popped out from our geometric analysis of it. So, all that you have to do to find what the new boundaries of integration should be is run them through the transformation just like you did everything else. The transformation is holistic. It takes that entire integral in terms of x and moves it to being an entire integral in terms of u. That's perhaps the most important thing when doing definite integrals, is making sure to transform the entire integral, because if you don't change those boundaries, you will get the wrong answer, just straight up. Okay, hopefully that was kind of a clear explanation on why the boundaries need to change and how to change those boundaries. Let's go do it for our previous example. Okay, so if we go back to the same example, we already know what the answer should be. The answer should be 8/3 minus the square root of 3, or is it the other way around? Yes, it should be 8/3 minus the square root of 3. And if we don't get that, something's gone catastrophically wrong. So let's do our U-substitution exact same way as before, making sure now to transform the boundaries in order to have the privilege of staying indefinite. So if u is 4 minus x squared and du is negative 2x dx. Side note, the du is essentially a geometric tool that's keeping track of any stretching and squishing that's going on. Yeah, because the u-sub just says, oh, shift to the new coordinates, but if things get stretched or squished, the actual area gets kept track of by du. And that's why that's an important thing to do. Okay, that's the side. So, we remember we wrote that same substitution of, this is 0 to 1 of negative 1/2 times negative 2x squared root of 4 minus x squared dx, so that the u sub would go kind of nicely. Now, let's actually do the substitution. This is the integral from our new lower to new upper bound of negative 1/2 u to the 1/2 du, for the exact same reason as in that previous example. So the question is, what should these new lower and upper bounds be? Well, what we're going to do is we're just going to plug the old lower and upper bounds into our u substitution. So our new u sub a is 4 minus 0 squared, which is 4. And our new u sub b is 4 minus 1 squared, which is 3. So now this is the integral from 4 to 3. Because that's our new lower, that's our new upper, since they correspond to the previous lower and upper. The integral from 4 to 3 of negative 1/2 u to the 1/2 du. Or in other words, negative 1/2 times the integral from 4 to 3 of u to the 1/2. Now, let's say you don't like having 4 be your lower bound and 3 your upper bound, because 4 should be larger than 3, so this should be on top. Great. That property of definite integrals that says, hey, the integral from a to b of f of x dx is equal to the negative integral from b to a of f of x dx. Now, this is the situation where stuff like this is useful, because it says you can flip those boundaries of integration at the price of a negative sign. So this is equal to, okay, a negative times a negative will be positive. So we're going to have positive 1/2 times the integral from 3 to 4 of u to the 1/2 du. Okay, that's something we know how to evaluate using Tyrol. This is equal to 1/2 times 2/3 u to the 3/2, going from 3 to 4. And because we've stayed in definite integral terms, we don't actually have to transform back into x world. That's the advantage of method 2, is you don't actually have to transform back into x world, because you've kept track of everything, all that numerical information, by changing the boundaries. You might say, well, what if I want to change back into x world? Fine. As long as you make sure to change the boundaries back as well. Either work fully in u world or fully in x world, I don't care which, both will give you the same answer, but you can't mix and match, because then things start going wrong because you're trying to apply one set of conditions to the wrong world. So let's stick in u world for now. 1/2 times 2/3, this gives you 1/3 times what? 4 to the 3/2 minus 1/3 times 3 to the 3/2, which by the exact same analysis as the first method gives you 8/3 minus the square root of 3. We got the same. Now, if you want, as I said, you could shift back into x world and you could say this is the integral from 1/2 times 2/3 of x, 4 minus x squared to the 3/2, but you'd have to make sure to plug the u sub back through as well, and you get it from 0 to 1. So, same exact answer. I prefer to stick in u world when I do stuff this way, just because it's less computational steps and I have less risk of accidentally losing track of something. But yeah, so by performing the proper substitution on the boundaries, we can stay in u world the entire way, and then we can only work there. It's a bit shorter, a bit faster. Alright, let's do another couple of examples. You might say, well, okay, what if I choose a bad u substitution that doesn't work fully the first time? How does that work with this whole definite integral thing? And the answer is exactly as this one does, where you just keep track of the boundaries of integration changing however many u-subs you need to make. So let's do an example. We'll do it with 1, where we choose kind of a less than optimal u-substitution, where it goes in 2 parts. And we'll do it with 1 great u-substitution, and we'll see how the variable boundary changes work in all those situations. Let's say we want to evaluate the integral from 1 to 4 of 1 over x times the natural log of x squared dx. Alright, so in general, when you see a natural log term, that's probably the best one to make your u-sub. So if I was looking at this, I would say, let's make the entire natural log of x squared my u and see what happens from there. But let's say you didn't see that. Let's say you just said, well, I want to make u x squared because it looks like it's on the inside, quote unquote. Okay, let's see what happens. If u is equal to x squared, du is equal to 2x dx, and our boundaries would change to being ua is equal to 1 squared, which is 1 again, and ub would be 4 squared, which is 16. So this would be equal to the integral of what? Well, let's see here. We have a 2x dx, but here we have a 1 divided by x. And that's bad because we don't even have a positive power of x to be working with. So maybe that would be a first clue that this isn't an optimal u-substitution. We could fix it though if we wanted. We've talked about multiplying constants in as a fancy 1. You can also do the same thing with variables as long as you're careful about it. This is 2x divided by 2x times 1 over x, natural log of x squared dx. Which, if you do your substitution in, this gives you integral from 1 to 4 of 1 over 2x squared times 2x natural log of x squared dx. So that's just rearranging what we've done. So we multiply by a fancy 1, we rearrange to get our 2x dx and everything like that. And then if you did the u-sub, that'd be the integral from now new lower and upper bounds 1 to 16. 1 divided by 2, what's x squared in terms of u? Well, it is just u. So we have 1 over 2u times the natural log of u du. That's our u. That's our du. Great. So it was workable u-sub. Multiplying by this 1 might not have been an obvious choice though, which is why this is perhaps a less than ideal choice of u-substitution. We'll do the ideal one next. Well, not next in this example. When we redo this example, we'll do the ideal one. Okay. Well, I still don't know how to evaluate this integral. I have a natural log divided by something else. I don't know how that works. I don't know what the integral of natural log looks like. So maybe it's time for another u-substitution. Maybe I say, well, okay, let's try making natural log my substitution. Since 1 divided by something looks like a lot like the derivative of a natural log. So that's a natural choice for like a dv. So let's do a v substitution from u world into v world, where we'd say v was the natural log of u, and then dv would be 1 divided by u du. So that's looking a little bit better since this is kind of the same format as our definite integral here. Well, what would our new upper and lower bounds be in v world? Since we're shifting from u world to v world, we have to change the bounds again. va would be the natural log of ua, natural log of 1. Natural log of 1 is 0. Standard property of natural logarithms. vb would be the natural log of 16. You could simplify that as like 4 times the natural log of 2 if you wanted. I don't particularly care. Works out the same. So if we did our v substitution, 1 over 2u is really 1/2 times 1 over u. So now we're automatically going to be able to do our v sub, and we get 1/2 times 1 over u du is our dv, natural log of u is our v, so we'd have 1/2 v dv. Cool. An integral we know how to do, and our boundaries would be 0 to the natural log of 16. Great, we know how to do that. This is 1/2 times the integral from 0 to the natural log of 16 of v dv by a scalar multiple rule. Power rule now says this is 1/2 times v squared over 2, going from 0 to the natural log of 16. And now, here's the advantage of working in definite integral world instead of in indefinite integral world, is you don't have to shift back. If you wanted to shift all the way back to terms of x, you'd have to go back from v world to u world, and then back from u world to x world, and it just gets too complicated. But because we're working in v world, where we transferred the bounds of integration over, we can just continue working here. And say this is 1/2 times 1/2 is 1/4. So we'd have the natural log of 16 squared divided by 4 minus 0 squared over 4. And that's just 0. So we'd end up with the natural log of 16 squared divided by 4. There we go. Alright, make sure you have this down. I'm going to erase it and redo the example with a better choice of U-sub. Let's say you're a little more used to definite integrals, and you figured out a better U-sub. And you said, oh, what if I let u be the natural log term? Since that's pretty common, letting u be the entire natural log term no matter what it is. Unless, of course, the natural log is like itself being squared or whatever. Well, no, actually, even then, especially then. Don't know what I'm talking about. Alright, so we let u be the natural log of x squared. Then what would du be? Du is the derivative of this thing, dx. And the derivative of the natural log of x squared is the derivative of x squared divided by x squared. So we get 2x over x squared, yes. Or in other words, 2 over x dx. So now we're starting to match our pattern. We have an entire u, and we're only a multiplicative constant away from having our d. So if we run this u-sub, let's get that 2 in there by multiplying by 1/2. This is 1/2 times 2 over x, natural log of x squared, dx. Run the u-sub. We need to figure out our new boundaries. In this case, our ua would be what? Well, we're plugging into this U-substitution. So we plug 1 into this. It's the natural log of 1 squared, which is the natural log of 1, again, which is just 0. And then U sub b would be the natural log of our old upper boundary squared. So it would be the natural log of 4 squared, which is the natural log of 16. And we'd have 1/2 times u, and then the 2 over x dx is our du. Oh look, so it's the exact same integral in v world as we had previously. Doesn't matter that this variable is u instead of v, as long as everything else about it is the same. The boundaries are the same, and the actual expression is the same. So we know we're going to get the same answer. We're going to be okay. Let's just do it to make sure everything works. This is 1/2 times the integral from 0 to the natural log of 16, u to u is 1/2 times u squared over 2 going from 0 to the natural log of 16. And look at that, that's going to be the exact same as up there, and it all works out beautifully. There we go. All right, let's do another few examples like this. I'll erase this stuff since you've already seen it before. For our next example, let's do the integral from 0 to 2 of x divided by x squared plus 1 dx. Alright? We have something on the bottom, and then the derivative of x squared plus 1 is 2x, so we have something close to that on top. That's probably a good use of. So if we let u equal x squared plus 1, then du would equal 2x dx. Yes, it's all coming together. Our new lower bound, in this case, would be 0 squared plus 1, which is 1. And our new upper bound would be 2 squared plus 1, which is 5. Alright? So then, in terms of u world, in terms of x world, we need to get a 2 in there first. This is the integral of 0 to 2 of 1/2 times 2x over x squared plus 1 dx. Now we have all the pieces parts necessary to do our substitution. This is going to be the integral now from 1 to 5, lower, upper, of 1/2 times, this is our u, then we have 2x dx, that's our du. And we're just left with a 1 on top. Pull out the scalar multiple, and we know how to integrate this. The integral of 1 over u is the natural log of the absolute value of u. That's a standard rule that you should have memorized. So this is natural log of the absolute value of u as u runs from 1 to 5. Alright? Evaluate the actual integral. This is 1/2 times the natural log of the absolute value of 5 minus 1/2 times the natural log of the absolute value of 1. Okay, well what's the natural log of the absolute value of 5? Well, the absolute value of 5 is just 5. Absolute value of 1 is just 1. And the natural log of 1 is 0. So we're just left with 1/2 times the natural log of 5. Since that is 0. Alright, this would be our final answer. Okay, let's do another example. So, I mentioned more than one definite integral rule, right? The one integral from a to a, that's kind of a trivial rule, but I also mentioned that splitter rule. Integral from a to b of fx dx is equal to the integral from a to c fx dx plus, specifically, integral from c to b fx dx. For any c in between a and b. Where's that helpful? When do we ever want to actually use this? Let's see an example. So I guess we've kind of shifted away from this for now. We can do more examples of it in class some other day if you guys want. Let's let g of x equal x squared minus 4 when x is less than 0 and x plus 3 for x greater than or equal to 0. So we have a piecewise function. If we were to graph g, it would look roughly like this. We have x squared minus 4. X squared minus 4 there, open circle, closed circle at like 3-ish. And that would be negative 4, that would be positive 3. Alright, so that's a rough graph of g of x. And let's say we wanted to evaluate the integral from negative 2 to 3 of g of x dx. So if we wanted to find, this would actually be negative 2, so that works out properly. And then 3 would be like here. So we want to actually find that given area, because that's what's said by this integral from negative 2 to 3. Well, we want to find that signed area, so it's really that area minus that area. How do we do it with definite integrals? Well, I can't just straight up put in a formula for g of x, because g of x's formula changes as we go from this region over to this region. The integral is not behaving the same way, so we can't just integrate a single function. But what we can do is we can use our splitter rule to our advantage. And we can say this is equal to the integral from negative 2 to 0 of g of x dx plus the integral from 0 to 3 of g of x dx. And you're like, sure, that's true because 0 is between negative 2 and 3. Why do we choose to split at 0? Because 0 is the place where the function splits. Anytime we have a split in the function, we can split the integral, and now we can handle the integrals in chunks where we do know a single formula for g of x. Because this is the integral as x runs from negative 2 to 0, and when x is below 0, which it is as it runs from negative 2 to 0, g of x looks like x squared minus 4. And as x runs from 0 to 3, positive x values, g of x looks like x plus 3. You might say, okay, but here it's a less than, here's it's greater or equal, so why the split at 0? Because it doesn't actually matter which side 0 goes on. The geometric reason for that is if I drew a straight line at 0, it has no area, so it doesn't matter if I toss it in extra on one of them. The analytic reason is that whole integral from a to a of f of x dx is equal to 0. All that means is you can split it properly and you can put the formulas in and it works fine. Don't worry about the less thans. Alright, so let's actually evaluate this integral. I can just use the sum rule. I don't even need to make U-subs here. I can just use the sum rule to split those up, making sure to keep track of the boundaries of my integral the whole way through. And we get that this is equal to the integral from negative 2 to 0 of x squared dx minus the integral from negative 2 to 0 of 4 dx plus the integral from 0 to 3 of x dx plus the integral from 0 to 3 of 3 dx. Power rule and constant rule on each of these, combined with the fundamental theorem of calculus, states that these are x cubed over 3 as x goes from negative 2 to 0, minus 4x as x goes from negative 2, 0, plus x squared over 2 as x goes from 0 to 3, plus 3x as x goes from 0 to 3. That's equal to what? Well, 0 cubed over 3 minus negative 2 cubed over 3. Making very sure to keep track of all the minus signs flying around because there's a lot of them. Minus 4 times 0 minus 4 times negative 2 plus 3 squared over 2 minus 0 squared over 2 plus 3 times 3 minus 3 times 0. Alright, computing each of these chunks individually, you have 0 minus negative 8/3, so this is 8/3, minus 4 times 0 plus 8, so we're going to have minus 8, plus 9 halves, plus 9. Alright, and if you do all that out, what do you get? You get negative 16/3 plus 27 halves, which is negative 32/6 plus 3 times 27 is 60, 70, 81. 8 minus 32 is 51 minus 2, 49. Let me check that with a calculator, make sure my mental math is correct. How about that? It was. Good news, everybody. So, 49/6 would be our final answer for this. So yeah, whenever you're trying to evaluate the definite integral of a piecewise function, split it in pieces with our rule for doing that, and then it all works out. Alright, so you might say, cool, I can now do all of these things with definite integrals, and I get that they represent the area under the curve, but why else should I care about definite integrals? Well, one of the most important things you could do with a real-world function is find out, okay, on average, how's it doing, right? Stock market goes up and down, but really I care about a general average for where it's at for the day. So how do we find information like that? Well, it turns out definite integrals are going to be our way of doing so. Average value of a function is one of the primary real-world applications of definite integrals. So, I'm going to provide a formula for average value first, and then we'll discuss why does this formula make sense. Suppose f is integrable on a b. Then the average value of the function on a to b, or your book might say over a to b, same thing. It's saying, hey, if you have a function on a region, what's the average value of that function on that region? This being the average. The average value is 1 divided by b minus a times the integral from a to b of f of x dx. Side note, this also holds for open intervals. So if somebody gives you open interval from a to b instead of closed interval from a to b, it'll still work out. All right. So that's the definition of average value. But why does it actually make sense? So I'm going to kind of handle this loosely since we don't really have the tools. Well, we have the tools. We don't have really the mathematical maturity yet to formally prove why this is holding, which is why I'd say this is definition, not theorem. But what's actually going on with this definition? Well, let's recall, we'll address it in a few ways, hopefully one of them will make sense. The average of a finite number of things. Let's say a set A1 through AN. So you have n things, and you're trying to find the average of them. It's going to be A1 plus all the way up through AN, divided by n. You take all the things, you add them together, and you divide by how many there are, and that gives you an average. So how does that correspond to integrals? Well, you can think of the integral of a to b of a non-negative function. This will hold true for any function, but you can think of it as this area, right? So what is that area really? Well, it's saying, hey, that area is kind of adding up all these infinitely thin lines, these values of the function. That's essentially what that's doing. And if you think of it as the limit of Riemann sums as the number of rectangles goes to infinity, this also corresponds to that. Your book discusses that a little more in depth as well. So yeah, look at that if this explanation doesn't make sense. But yeah, you're essentially adding together all these infinitely little slices, and that gives you the area. So then how do you find the average value? Well, you need to divide by how many, quote unquote, things there are. And if you were to go take Math 550 here, something called measure theory, you would say, well, really the quote unquote how many things there are in an interval, the measure of that interval, is its length, which is b minus a. So now the average value is 1 over b minus a, the how many things there are, the 1 over n, times the integral from a to b of f of x dx, which is the summing up of all of those values. So that's one way to think about this definition. What's another way, in case you don't like this one? Another kind of geometric way to think about what's going on here. What if f was a flat line? Right, so we have a flat line between a and b. Well, then the average value is just the value of the function. So if we have a constant function, the average value is just the value, right? Makes sense. Well, how would you find it? Geometrically, that's a rectangle. So how would you find that side? Well, if you're given the area and you divide by the width, you'll get that length, which is the side we're looking for, right? We're looking for how high that is. So that gives you precisely 1 over b minus a times the integral from a to b of f of x dx would be the value. That's what we're looking for. But functions aren't all constant. What if they're squiggly? So let's say between the same a and b, you have a function that squiggles like that. What I'm hoping to convince you of is that this area is what's measured by the integral. It's this area under the function. What I'm hoping that you can believe without me formally proving is that if you draw a line at the average value of a function, that the area that you lose here, right, that doesn't get picked up by the integral, is the same as the extra area that you pick up above that average. And if you believe that those two things are the same, then the exact same idea is going to hold, because, well, what's the area of this, or what's the height of this side? 1 over b minus a times the area of that rectangle, and if that area under the red is the same as the actual area that measures the integral, then we get the exact same formula. So, hopefully you can believe one of those two explanations. That's why this definition makes sense. And if you don't care about why the definition makes sense, and you just want to use it, let's do it. We'll do 2 examples and then I think we'll call it good for this video. Let's find the average value of f of x equals 1 minus x squared on the interval -1 to 1. Alright? Well, they give us the problem. We set it up immediately like the definition. This is going to be the integral of 1 is our b. So we have 1 over 1 minus our a. In this case, our a is -1. Side note, it's okay if this ends up being a negative number out in front. The average value of the function could be below 0, and that's okay. Alright, so you have 1 over 1 minus -1 times the integral from -1 to 1 of 1 minus x squared dx. No, it's 1 minus x squared, not 1 minus x squared, so we can get away without doing U-sub. This is 1 over 1 plus 1 is 2. So it's 1/2 times the integral from -1 to 1 of 1 dx minus 1/2 times the integral from -1 to 1 of x squared dx, right? That 1/2 has to distribute. So what's that? Well, that's 1/2 times x, as x goes from -1 to 1, minus 1/2 times x cubed over 3, as x cubed goes, or as x goes from -1 to 1. So this is 1/2 minus -1/2 minus 1/2 times 1/3 is 1/6. So you're going to have 1 cubed over 6 minus -1 cubed over 6. That's 1. And then you'd have 1/6 plus 1/6, which is 1/3. So you'd have 1 minus 1/3. 2/3. So what's that saying? In terms of picture. In terms of picture, what that's saying is if you drew 1 minus x squared between -1 and 1, it would look something like this. That the average value between there would be roughly here, at 2/3-ish. Hopefully that, maybe it's a little lower for 2/3, but right, it's kind of here. It's going to have some amount of time above it, a lot of time above the average, and then a short amount of time very below the average, and that all balances out to give you 2/3 as the average. All right? Let's do another real-world example, and then we'll call it good. Oh boy, there's a lot of writing. New piece of chalk for that. All right, so for this example, let's say that a bank charges student interest loan rates, or student loan interest rates rather, because the loans certainly aren't in your interest. According to the formula, R of t is equal to -1/2 t cubed plus 21/4 t squared minus 18t plus 25, where t runs between 0 and 5. So this formula is only valid for t between 0 and 5. Where R of t is measured, or rather, is the annual percentage rate. And t is measured in months. What is the average loan rate for months 0 through 5? And then how about 1 through 3 as well? Alright? Well, if we're trying to find the average value for months 0 through 5, that's as t runs from 0 to 5, because t is measured in months. Therefore, our answer for months 0 through 5 is we're going to take 1 divided by 5 minus 0 times the integral from 0 to 5 of r of t dt, which is applying the sum rule, scalar multiple rule, everything like that. That's 1/5 times the integral, 1/5 times 1/2 integral from 0 to 5 of t cubed dt, -1/2, that's a very important distinction, plus 21/4 times the integral from 0 to 5 of t squared dt minus 18 times the integral from 0 to 5 of t dt plus the integral from 0 to 5 of 25 dt. So we have the 1/5 in the front times each piece apart. 1/2 t cubed, 1/2 t cubed. 21/4 t squared, 21/4 t squared. Negative 18t, negative 18t, 25. Alright. Let's evaluate all those integrals. Distributing the 1/5 out and applying the power rule to each of these gives us negative 1/10 times t to the 4th over 4 as t runs from 0 to 5 plus 21 over 20 times t cubed over 3 as t runs from 0 to 5 minus 18 times t squared over 2 as t runs from 0 to 5 plus, 18 fifths. 1/5 times 25t as t runs from 0 to 5. And if you do all of that arithmetic out, which I recommend you try on your own, making sure you're practicing at keeping track of all your minus signs and everything, you should end up with exactly 8.12. Alright, so once you have all this down, once you've convinced yourself that it is in fact 8.125, let's take months 1 through 3. And I'm going to erase this half so we have all our problem statements still. So months 1 through 5 would be 8.125. And then months 1 through 3 in this case, well, the only thing that's changing is instead of going between 0 and 5, we're going between 1 and 3. So it'll be the integral from 1 to 3 of r of t dt times 1 divided by 3 minus 1. So this is 1/2 integral from 1 to 3 of r of t dt. Exercise. Compute this. It should be 6.75. So that's what you should get at the end of it. Try it on your own. Make sure you're getting all this right. Okay, so what does this tell us that our actual average loan rates are? For months 0 through 5, the average loan rate is 8.125%, since R of t is measured in percentages. And for months 1 through 3, the average loan rate is 6.75%. Alright, I think that's all for this video. So hopefully at the end of this you've learned a couple things. One, if you do U-subs with definite integrals, if you want to stay in definite integral world, change the bounds as well. Secondly, you can use the splitter rule for definite integrals to evaluate the integral of a piecewise, definite integral of a piecewise function. Indefinite integral is its own thing. And finally, you can use definite integrals as a tool to find the average value of a function on an integral. Alright, have a great rest of your day.